Lesson 7, displacement time graphs. We will be able to construct a displacement time graph. On the top right here, while you're copying that down, I'm going to read this. On the top right, we've got a topic from one of the left. On the top right, we've got one of the stolen ideas tasks that I thought I would talk about, which is Ada Lovelace. Ada Lovelace was born in 1815. Was an English astronomer and mathematician who was known to be the world's first computer programmer, which is a bit odd if you think about it. It's like 1815, they didn't even have computers. She worked with the inventor and mathematician Charles Babbage, who served as her mentor and developed the early version of the computer. Now, if you think about a computer in those times just meant a person that computed numbers. So I think this was the first autonomous computer, the first computer that worked on its own. The first computer that worked on its own didn't actually use electricity, it used gears and those sort of things to make it work. It's actually kind of interesting. And the device that they came up with was called the analytical engine. Ada is thought of to be one of the first to theorize programming concepts such as loops and numbers representing letters. For this machine, which would be found useful about a century later, Ada published a paper which translated a French article and a lot more of her own concepts and information to it. However, many believe that Lovelace did not create these concepts herself, but stole them off her mentor, Charles Babbage. The reason this is believed to be is because Babbage had aided her in publishing her paper and provided her with ideas and concepts of her own. People believe she took on as her own. Okay, cool. So this is a bit interesting because in the past they've given this to students. So this was done by, I think with Jake, this was your one, if you're listening. This was done in the past. Usually people say, well, Ada didn't receive her credit, but this time, because they're giving you guys a lot of freedom, Jake's actually interpreted this differently. He's actually taken the view that Ada stole her arguments from Charles Babbage, which is a bit of an interesting approach to this question, which I kind of like. But yeah, she is still regarded as the person that came up with computer programming. So yeah. What did we do last time? Sorry about that. Well, I'm not sorry about that. It's just a little bit about engineering. It's a little bit important. So what did we do last time? Last time I had you guys, what we did was we looked at displacement versus distance, and then what we did was, the very last time I had you, was displacement in two directions. We looked at what happens if you go in two directions, like north and then west, or north and then east, or something like that, and how do you describe those. Then what we did was, yeah, that was about it. And then I gave you guys some time to work on motion 1, I believe. So today what we're going to talk about is displacement time graphs. So you guys may have seen displacement time graphs before. I hope you have, because it'll give you an advantage. But we're going to construct our own displacement time graph. We're going to spend some time discussing it, talking about the parts to it, and so on and so forth. But what we're going to do, and normally what I would do is I would do this with you at the exact same time. But unfortunately, that's going to be a little bit more challenging. So what we're going to do today is we're going to construct a displacement time graph. And I'm going to ask you first, I'm going to give you guys a bit of a story. Okay? The very first thing I want you guys to do is I'd like you guys to write down this story. Because what we're going to do is we're going to draw this story afterwards. So the first part of the story is, it's a story about a mouse. So I'd like you to write this part here down. A mouse takes 4 seconds to walk 2 meters to a piece of cheese. You can maybe write 4 sec, SEC, you can't be bothered writing 4 seconds. You can use any abbreviations you want, but I just wanted to copy this starting part here down. Okay. So after the mouse goes these 2 meters, the mouse nibbles some cheese for about 2 seconds. So just add that to the story. Okay, what's next? The mouse carries the cheese 1 meter towards its hole. Oops, sorry. What's next? The mouse hears a human and runs to its hole in 1 second. The last little bit is this bit here. No, that's it. So these are the 4 steps, right? The mouse takes 4 seconds to walk 2 meters to a piece of cheese. The mouse nibbles the cheese for 2 seconds. The mouse carries the cheese 1 meter towards its hole. The mouse hears a human and runs to its hole in 1 second. Can I get someone to tell me what is the total time taken for this whole story? In chat or out loud, don't care how you want to do it. How long does this whole story go for? 11 seconds? Yeah, I count about 11 seconds. 4 plus 2 makes 6, plus 4 makes 10, plus 1 makes 11. Yeah, good, 11 seconds. And what is the furthest distance from the hole the mouse actually goes? Someone else, someone other than Dylan. Thank you, Dylan, for that though. Anyone in chat, up to you. Furthest distance from the hole. Thank you. You went 2 meters. You went said as well. Sorry, Dylan. So you weren't the only person this time. So yeah, cool. So now what we're going to do is we're going to plot this. And what we're going to do is we're going to create something called the displacement time graph. Now you guys should know how to do this already because of year 10 science. But if you don't, that's okay. Or if you didn't do very well at it, this is your chance to improve. So how do we do this? Well, all right. I've got myself a ruler here, and I'm going to measure, I'm going to rule a line here. And then I'm going to rule a line across the bottom. Now, because I've got the whole page here, I can take up as much space as I want. And but you guys may have a little bit less space, so you guys might not take up this much space. I'm going to call this one down the bottom time. I'm going to call this one at the bottom displacement. So I'm going to give it the symbol X. Okay. Now the bottom, I'm going to do marks every 2 centimeters. So let's see. We've got we're going to call that 2, 4, 6, 8, 10, 12. Now you guys can do it your own. I'm using a ruler because I've got access to a ruler. Usually when I do these, I do them freehand. But if you guys want to do the other one, we're going to do the same thing. We're going to do, but I'm going to go up every 2 centimeters. And we call this 1, 2, 3, because I don't need to worry too much about the vertical because it only goes 2 meters away. And it only takes 11 seconds to complete the whole journey. So it's actually not going to be too difficult. So let's now work through how we would then plot this. The first part, a mouse takes 4 seconds to walk 2 meters to a piece of cheese. So that means the mouse is moving 2 meters. Okay. And it takes 4 seconds to do that. So if I go across from here, you get to 4 meters. That's there. Oops, crap. Okay. So to get to this 4 meters takes 4 seconds to go 2 meters. That means let's start here and we'll draw this line in here like that. So that line here represents the motion of this mouse. This mouse is moving away from its hole because it's going from near to far, and it's doing that. And by the way, it's going from near because that's the small values of x. We've got near. For large values of x, we've got far away. It's moving from near to far, and it takes 4 seconds to do that. That gives us our first leg of the journey. The second thing is that the mouse nibbles the cheese for 2 seconds. Can someone other than Dylan, who's doing a really good job today, thank you, Dylan, can someone other than Dylan tell me when the mouse nibbles the cheese for 2 seconds, what happens to the mouse's motion? It stops. Yeah, the mouse will be still. So if it stops and it's still, what does that mean about its displacement? Will its displacement go up or down? It will be 0. It'll stay the same. Thank you. It'll be the same. So if I go for 4, if it's staying the same for 2 seconds, that means from 4 to 6, it's not going to change its displacement. So we end up with this straight. Oops, we end up with this straight line here. Okay. So, all right, so we end up with this straight line here, which is where it's stationary, it's not moving. The mouse carries the cheese 1 meter towards its hole in 4 seconds. Okay, so the mouse travels 1 meter towards its hole in 4 seconds. Okay, so 4 seconds later, so if we've got 6, the next time we'll go look at is 10. I'm 1 meter closer towards the hole. So where do I draw that line? Do I draw that point up at 3 or do I draw that point up at 1? Did someone give me a suggestion? UNC said 1. Why is it 1 and not 3? How do we know this line goes down and not up? Because you're getting closer towards the hole. Really good idea. We are moving towards the hole. Because we're moving towards the hole, we have to draw this line that goes down towards the hole. We're going from far away to near. Sorry, you guys can't see that. We're going from, oopsies, now you can't see anything. Oopsies. We're going from far away to near, and that's why this line here slopes down. Now the next part, and the last part is this. The mouse hears a human, runs towards its hole in 1 second, okay? Someone other than Ewan or Dylan, someone new, someone other than Everest as well. Can I get you guys to tell me, in that 1 second, is this line going to go down to the bottom or up to 2? It travels 1 meter, or it says it travels to its hole. So is the line going to go up or down? Someone in chat, other than the 3 that have already responded, someone new. maybe Elaine, maybe Eric, maybe George, maybe Jake, maybe Oliver. It goes down. Yeah, thank you, Eric. It does go down. It goes down to the bottom line. And it does that in 1 second. So from 10 to 11, it shoots down like this. And then that's the end of the story. So this here is what we refer to as a displacement time graph. And it gives us an idea of what's going on here. We can say for this time, the mouse is moving away, but for this time here, the mouse is moving towards. It is moving towards at different speeds, at different times, but that's, that's fine. That's in general, we get the idea. Can I get someone new? Maybe Elaine or George or Leoa. Can you guys tell me, when is the mouse moving? This is actually an interesting question. When is the mouse moving the slowest? So someone new. I'd love for like Elaine to type something. That'd be great. But I don't care. I'll take anything. I'll even take Ricardo. I know you were here. Oh, Oliver. Oh, cool. Thank you. When he is not moving at all, when he is carrying the cheese, or when he's carrying the cheese. So Oliver's got a point, and I think Oliver picked up. He's like, oh, I can see Mr. Greer is trying to confuse us. And then I'll be honest, there was a little bit of something like that here. You could get technical, and you could make an argument that the slowest the mouse is moving is right here, because at this point the mouse isn't moving, so he's moving the slowest. But that, you might say, well, he isn't moving, so you can't say he's moving the slowest. So the other idea would be this time here. If you look at this time here, the mouse travels 1 meter, but it does that, the mouse does that 1 meter's travel in 1, 2, 3, 4 seconds. That mouse for this point of time here is traveling 1 meter in 4 seconds. So 0.25 meters per second. Probably negative because it's going towards the hole. Compared to, when is the mouse? Can I get someone to tell me? Let's get Thomas. I know you're here. Thomas, when is the mouse moving the fastest? This should be relatively easy. When is the mouse moving the fastest? Thank you. 10 to 11 seconds. You're right. This is the fastest point, because in this point, he's traveling the whole meter, again, just like in this one, but he's doing it in 1 second. He's actually moving 1 meter per second. That's actually when he's moving the fastest in the whole time. Even faster than this. This is actually 0.5 meters per second. So this tells us a lot about where the mouse is. We can also figure out how far the mouse has gone. The mouse has gone a total of 2 meters away from the hole. The mouse has traveled 4 meters in total. It has gone 2 meters away and then 2 meters back. So it's 4 meters in total away from the hole. 2 meters away, 4 meters distance traveled. Displacement is 0 because it starts the hole and ends of the hole. There's a lot of information we can get from just one graph, and that's what the lesson here today is all about, is how can we get information from the graph. And I think that's it. What time have we got here? My things I've got here saying we're at 10 to, no, we're not. We've got time. Sorry. Whoosh, I thought we were, sorry, we've got a little bit of time left. All right, I panicked. Panicked. There was a panic. I'm having a panic. So I had a panic because I was thinking it was 10:36, and I thought, oh, well, that's the end of period 2. We're in period 3. Period 3 ends at 11:48. So we've got another 13 minutes left. So we've got enough time to talk about one extra thing. So thank you guys. Thank you for everyone that contributed to that. It was really good to see some people here to contributing. Yeah, and even Elaine contributed as well. So yeah, it took me a second before I saw your comment, Elaine. So sorry about that. You did actually say something though. So, and the last question here at the bottom is, do mice walk? I don't know if mice actually walk. I don't know if that's, if technically you would say that. Maybe crawl, maybe scuttle, I don't know. So, what we were doing at the very end there, where we were measuring how much the displacement had changed over time, we calculated a bunch of different speeds there. We said, well, 1 meter per second, that's really, really fast, whereas -2 meters per second, that's pretty slow. So, also, guys, I really hope I didn't tell you to do it, but I hope you guys copied down or did your own version of that graph. Now, ladies and gents, if you did not do your own version of this graph, then that becomes your homework task, is to draw a copy of this graph. I did not tell you guys you must draw this down, but hopefully you guys did something, you drew this down, either as I was doing it or afterwards. But if you didn't draw this down, you need to do this drawing afterwards, make sure it's the same measurements. Now, I didn't need, one more thing about this graph before I move on, is I've tried to take up a large area of this page. That's why I didn't go up to 10, I only went up to 3. And here, I tried to go as close. And the best way to take up as much space in the graph as possible is to know how long it goes for and what's the furthest distance away. So that's just something to keep in mind when you guys come to draw these types of graphs. So I want to talk to you guys about this next idea. So we've talked about displacement a lot. The next idea to talk about is speed versus velocity. So this is got a fair bit of stuff in the slide. So we've got a little bit of time to do it, so let's talk about it. So copying this down if you wouldn't mind, or again, like taking notes or taking a photo, but regardless. Speed tells us how far an object moves in a given amount of time. It's like saying how fast it is. Okay, so how far have you moved and how long did it take you? Did it take you 2 years to move 1 meter, or did it take you less than 2 seconds to move 2 meters? Velocity is a step up from speed. Velocity is like the upgraded version of speed. Velocity tells you not just how fast you're going, but what way you're going. Usually velocity will have either a positive or negative value, and so yeah. Both of them use units of, can someone tell me what's the units of speed? What are the units of speed? Someone, anyone this time? Meters per second. Thank you, Oliver. Meters per second. So they both use the speed, the units meters per second. There are other units of speed. Kilometers per hour. Let's put kilometers per hour. Let's add that to our list. We could even have, we'll either go miles per hour. But yeah, all of these are different. They all measure speed. I will point out to you guys just really quickly, sometimes textbooks won't write meters per second like this. They'll actually use index laws and they'll write meters per second like this. Sorry guys, I haven't got a pen, so I'm just trying to do this with a mouse. MS risen to the power of -1. You might be like, whoa, 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 what? But s risen to the power of -1 just means you're going to go m over s to the power of 1, which is just going to be m over s, which is the same thing. Just be aware that sometimes they do it differently. Velocity has to have a direction, so you can say north, you can say 20 degrees from the horizontal, you could say forwards, you could say backwards, you could say down, you could say away from the mouse hole, towards the mouse hole, doesn't matter as long as it's got some way to give a direction. Speed is a scalar and velocity is a vector. Velocity being a vector is easy to remember. It's pretty much the same. Scalar, speed. Displacement and distance are a bit harder to do. Right, I'm going to give you guys about 30 seconds to finish copying this down. If you guys need a little bit longer, let me know. But then we're going to change the slide. I'm going to try and do, what have I got? I reckon I've got time to finish off all 4 slides. We've only got 2 slides left, so we're going to try. Okay. So that's speed and velocity. That's actually what we're going to be working on maybe next week, maybe this week. I'm not sure. I haven't decided how we're going to do tomorrow's lesson. I'm not sure if we're going to be doing any work at all and it's just going to be completely spent on you guys working on motion 2, or if we'll do a little bit. I haven't decided yet. Maybe I'll do a little bit. Maybe I'll introduce you to converting units and that'll be it. So the next thing I do want to finish up on, almost finish up on, as I said, I've only got about 5 minutes left, so I probably will skip one little thing. I'll probably skip this last slide here because there's a bit too much stuff here, but I will talk about this. We're going to talk about delta. Now you guys, delta is a Greek letter. Okay, what does delta look like? It looks like this. So, thank you. Sorry. Sorry about that. I just got a package and I was just a bit distracted just then. So delta. Delta is a symbol that is a Greek letter. What delta means is delta actually means a change in something. You can use delta for anything in physics and maths. We use it all the time. So delta T means a change in time. Delta V means a change in velocity. Delta T could also mean a change in temperature. You can have a change in height with delta H. You can have a change in length with delta L. Whatever you want, you can measure with the delta. It's just a lazy way of saying that. So let me just, this will be the last thing I go through today. So we'll talk about delta T means a change in time. Delta V means a change in velocity. How do you calculate a change in velocity? Well, you take your final velocity and you minus your initial velocity. You could also have, we'll talk about it. We'll talk about it over here. You could also have a change in displacement. The delta X would be equal to your final displacement. Come on, final X minus your initial X. I'm not going, this is not going to be able to read this, I'm sorry. You get the picture. Now, just because I'm just going to be, it's going to help us later on, I will point out that you can rewrite, instead of writing final V and initial V, you can actually write your change in velocity as just V minus U, where V right? V means your final speed. And U, because the letter U becomes before the letter V, that means that U is your initial speed. That's what those letters mean. And then this, of course, means a change in velocity. It means a change in velocity. And that's it. Ladies and gents, I'm going to give you guys a little bit of time to copy this down, but it is, according to my watch, 11:46. So once you copy this down, you guys can leave the Zoom. If you've got any questions, queries, if you're running late on some of the things you want to talk about it, please send me an email. Otherwise, I will see you tomorrow, and we're going to wrap up the end of this lesson, and then I'm going to give you guys the rest of the time to work on motion 2. Okay, cool? Anyway, thank you guys for paying really close attention, and I will see you guys on Thursday.